Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the problem of finding the velocity, and you'll see that later on, the solution to this problem here is obtained by applying the idea of limits. Well, in this example here, we have a ball that is dropped from the upper observation deck of a tower, let's say 550 meters above the ground. And if the distance fallen after t seconds, so the distance here is described by this equation. So this is just a quadratic equation where the distance here depends on the time. So time here is in seconds, whereas the distance is measured in meters. Now, based on this information given here, you are asked to find the velocity of the ball after 5 seconds. Now, this is an example of a classic experiment, and this type of experiment originates from another experiment which has been done hundreds years ago. So this is just a little bit of history if you guys are interested in the historical mathematics or historical sciences. Well, in the 16th century, Galileo has famously demonstrated that when he dropped a 10-kilogram cannonball and a 1-kilogram stone, both of them strike the ground at practically the same time. And the result of this experiment has demolished the previous idea. So this is the idea, Aristotelian idea, that says when an object weighs 10 times as much as another, that object should fall 10 times faster than the lighter object. So this idea here has been demolished. Okay, right, back to our example here. Let's say you are interested to find the velocity of the ball after it is dropped 5 seconds from the deck of a tower. So velocity is given by this formula, which is you need to know what is the displacement and what is the time interval. So in other words, we need to know what is the distance at time t2 minus the distance at time t1 over the difference of time, which is t2 minus t1. Now, the problem that we have here is that the question given here doesn't explicitly stated the time interval. So there is no time interval here. In other words, the question is asking you to find the instantaneous velocity, whereas the formula that we have over here is the formula to find the average velocity. Okay, so let me just talk a little bit more about instantaneous velocity. So what is instantaneous velocity? As an example, speedometer is a tool that can help you to find what is the instantaneous velocity of the car that you're driving. So imagine you are driving a car and somebody asked you find the velocity of the car after 5 seconds. So what you can do is you can start counting 1, 2, 3, 4, 5, and after that 5 second, immediately you should be looking at your speedometer over here, and based on the reading, let's say you can see that the instantaneous velocity of the car is at 80 miles per hour. Okay, at about 80 miles per hour. So that's how you can find the instantaneous velocity. But if you go back to our example here, we don't have such machine, we don't have a speedometer to help you find the velocity of the ball immediately after 5 seconds. So what are we going to do is we are going to approximate, we're going to guess, we're going to estimate what we don't know, which is this one. We don't know what is the instantaneous velocity, and we are going to use the information that we have, or the knowledge that we have, which is we can calculate the average velocity in order to approximate what we don't know here, which is instantaneous velocity. Yep. And like I said earlier, average velocity is very simple. It is just finding the distance traveled, okay, the difference between the distance traveled over time elapsed, or the difference between the time. Okay, so what are we going to do now is, based on this table here, you can see there are different kind of time intervals. So for the first one here, the time interval is between 5 to 6. So if I can sketch the representation, maybe it looks like this. So this is from 5 seconds to 6 seconds. Now if it gets if you go on, you can see that, for example, this one here, the time interval is shorter. So that is from 5 to 5.05, and this one, it gets even shorter, and this one is the shortest time interval, which is between 5 to 5.001. So basically what it is doing is, if for this one, for example, the time interval is cut to between this and this value, for example from 5 to 5.1, and for this one here, it gets really short, perhaps somewhere here. So you can see that when the time interval gets really short, there is not much difference with what we are looking for, which is the instantaneous time where t is equal to 5. Okay, because the interval now gets really short, we are almost approaching the instantaneous time where t is equal to 5, which is what we are looking for, really. Okay, so now if you calculate the average velocity at all this time interval, you will expect that the average velocity at this interval here will approach the instantaneous velocity that you are looking to find. So that is only logical to think in that way. Yep. Okay, so now what we're going to do is we are going to calculate the average velocity. So for example, this is the first time interval. What we're going to do is we need this equation to find the distance. That is just 4.9 t squared. So this is, you can call this as t2, and this is t1. So the velocity is going to be the distance for t2, which is 4.9 times 6 squared, minus the distance for the time here, t1. So this is 4.95 squared, over the difference in time is going to be 6 minus 5. And if you calculate this, you will be able to get that the average velocity for that time interval is going to be equal to 53.9. So keep on doing this just to see how the number converges to a certain value. So for the last one here, so this is the 5th time interval. So the last one here, you can plug in the values 4.9 times. So this is the value of t2, which is 5.001 squared, minus 4.9. This is the value of t1, so 5 squared, over the difference of the time. It will be 5.001 minus 5. So when you calculate this, you will be able to get the result is equal to 49.0049. So based on this result here, you can guess that the instantaneous velocity is going to be very close to this value. So you can safely assume that it's going to be equal to 49 meters per second. Right, so as a conclusion, what we can say that limiting value of average velocities will be equal to instantaneous velocity, which you are looking for. So this is what you want to find. And what you have done so far is you calculate the average velocity. So average velocities is given here. So this is what you have done. You calculate the average velocities, and there is another word here which is limiting value. Why are we having this term over here? Is because you can see that the interval here gets shorter and shorter, so it approaches the instantaneous time. So the time interval here gets really short and it approaches instantaneous time where t is equal to 5. So we are talking about the limiting value. We are talking about the process of seeing a certain value gets closer and closer to another value. Okay, so now the whole process here is limiting value of average velocities. And finally, you can say that therefore velocity of the ball after 5 seconds is about 49 meter per second. Okay, so now in the next slide, I'm going to visualize what is going on here based on sketching the graph. Okay, so now how do you think the equation can be graphed? So what we have is the equation of d equals to 4.9 t squared, and if you want, you can think of it in terms of y is equal to 4.9 x squared. So this is something that everybody is familiar with, and we also know that if you have y is equal to x squared, the graph is going to be looking like this roughly. And therefore, if you introduce a constant right next to x, y is equal to 4.9 x squared, the graph is going to be vertically stretched. So it's going to be looking like this, more or less. Okay, so it has the same shape. It is just that the values are stretched vertically. Okay. Now, since x must be taking only positive value, because x here is actually representing time, there is no negative values for time, so actually the graph here is going to be just on this positive x and positive y. So if you sketch the graph for this function or for this equation, it will look like this. So we're just considering the positive value of t, and so the positive value of y-axis here, which is d. Okay, this is t. Right, now suppose you consider a point, so point P, where P is represented as A. You can choose any point, so let's say point P here represented by A, x is equal to A, so this is the value of x, and this one is the value of y. So if you have point A somewhere here, so this is the value of A, therefore you can find what is the value of y-axis. You can find what is the value of this function. So there must be you must be plugging A into this function. Yep, so you will get that the value of y will be 4.9 A squared. As simple as that. Now if you have point B, so let's say this is point B, you can think of it as having point A plus another distance. So you can think of it as point A here plus another distance. That distance is called h. So at this particular point, we can call this point as A plus h. Okay, does it make sense to you? So A plus the distance, which is h. So A plus the distance will give you another point that can be called as A plus h. So therefore, at this point, we can determine what is the value here, because we know the function. So we're just going to substitute A plus h into the function, and it looks like this, 4.9 times A plus h squared. So this is the value of y, and this is the value of x. Or this is the value of d, which is the distance, and this is the value of t, which is time. Okay, anyhow that you are comfortable with, it doesn't matter really. Now next, since we've got these 2 points here, you can calculate the slope of this secant line. So if you connect the dots here, you will obtain a secant line, and you should be able to find what is the slope because we have 2 points. Okay, so you see, you connect the dots here, you'll be able to construct a secant line, and based on that you can find what is the slope of the secant line. And obviously the slope of the secant line can be obtained using the usual formula which you have seen. So this is the formula which you have seen before. This can refer to point y2, this is point y1, this is point x2, and this is point x1. So this is the slope of the secant line. And I hope that you can see this formula is the same formula which is used to finding the average velocity. Okay, so the slope of the secant line is the same formula that you have used in finding the average velocity just now. Okay, and therefore what we have done just now is we started off with 6, the time interval between 5 and 6. Okay, so we started off with time interval between 5 and 6. That means you're talking about roughly at this point, 5 and 6. And then the interval gets closer and closer to maybe t between 5 and 5.001. So basically from 6 it is moving closer and closer towards 5. So in other words, when you are moving this closer and closer to 5, you are actually moving this point here closer and closer to this fixed point. So this is P, yeah, closer and closer to this one. And when you are doing that also, you can see that the distance h here will get closer and closer to 0. So h will be approaching 0. H will approach 0 when the value of interval 6 gets closer and closer to 5.001. And therefore, again, velocity at time t equals to a happens when h approaches 0. So what we have done just now, we have shown that the limiting value of average velocity is equal to instantaneous velocity, but instantaneous velocity is also equal to finding the slope of the tangent line at P. Okay, so by doing that, you can also find the tangent line at P. So let me just write down what we have done so far. We have shown that limiting value of average velocities is equal to instantaneous velocity. Okay, why? Because when you see that the interval gets closer and closer to this particular point here, you will get the instantaneous velocity at time t equals to 5. But by doing this process also, you will see that this is something which you have seen we did in the tangent problem. So when you move the point closer and closer to this fixed point over here, the slope of the secant line is similar to the slope of the tangent line. So therefore, limiting value of average velocity here can be said will be equal to the slope of the tangent line. Okay, so that is the conclusion here, which demonstrates that both problems, to find instantaneous velocity and to find slope of the tangent line, will apply the idea of limits. Okay, so that's the conclusion. We use the similar idea in limits in finding the tangent, okay, finding the tangent line to the curve at a particular point, and also to find the instantaneous velocity. Alright, I think that's all for now. Thank you very much for watching.